Welcome to Algebra 2. This is section 3.6, the concluding section of chapter 3 on quadratic inequalities. All right, for our introduction, as we've done in the past, here we've got the function f of x equals x squared plus 2x minus 3. Explain how you could use this graph to solve the inequality x squared plus 2x minus 3 is less than or equal to, oh, it's not f of x anymore, it's 0. Okay, so we want to solve that inequality. And just remember that f of x means height, okay? And the solution we're looking for is a range of x values. So I want you to pause the video, take a few, take a minute or so and try and come up with an explanation, and then I'll check back with you here in a few seconds. All right, let's have a look at this exploration. So we've got this function plotted over here where the height every time is following the function f of x based on different x inputs. Okay, we want to solve the inequality. Where is that function producing a height that is less than 0? So what x values give us a height that is less than or equal to 0? Okay, well, I see that here it is equal to 0, the height. And here it's also equal to 0, the height. It is less than 0 for this whole expanse. So all along that jagged green line that I sketched in, that's where the graph has a height less than or equal to 0. Okay, so how do we express that? Well, we're looking for a range of x values. This x value right here is -3, and this x value right here is +1. And if we didn't have the graph, we could do that by factoring or quadratic formula. We can find those zeros pretty easily. That's what we spent most of the chapter doing. How do we express our answer, though? So here we want x values that are between -3 and 1 and including those values. Again, less than or equal to means it's below or equal to. And at those two x values we described, the graph equals a height of 0. So we are going from -3 to +1. So -3 is where I start. I include my x, and then up until I get to 1, and I include that as well. So this is called a compound inequality. It's a way of expressing a range of numbers, pretty much. We could use interval notation from -3 to 1, and we use square brackets to include. But explain how we could use this graph. So we solved it, but how do we use the graph? Looked for x values where height, that's what f of x means, is less than or equal to 0. Mind my P's and Q's. But I really like this as an introduction because it, again, reinforces that idea that f of x, it means y, it means height on our graph. And when we replace that with a 0, we're comparing that graph to a height of 0. And in this case, it's not where is it equal, but where is it lower? Where does it have a lower height than 0? All right, our key concepts for today. How to graph a quadratic inequality. Well, first, we're going to graph it as if it were an equation. So as if it were containing an equal sign. Okay, once we have that graph, we either make it dashed for inequalities that are strictly less than or greater than, and it's a solid line if it's less than or equal to, greater than or equal to. Okay, and the reason being, if we have a dashed line, it means that's a border, but what's on that border is not included. So that's what ties in with those less than or greater than signs. After that, we're going to test a point, xy, inside the parabola to determine whether the point is a solution of the inequality. Okay, if that is a solution, then we will shade that portion of our coordinate plane. If it's not, we will shade the other portion. Now, it doesn't have to be a point inside, it just needs to be test a point, and that just determines whether or not we shade there. a nice point to choose is 0, 0. Just because it's very easy to plug those in and simplify. But if that's not available, we could choose like 1, 1. Now, you get to choose the point. Make it one that's going to provide the least amount of effort on your part. Okay. All right, so example 1, graph the inequality. Y is greater than or equal to negative 2x squared plus 9x minus 4. Okay, well, let's just go about this as if we were graphing a regular old parabola. So axis of symmetry, we would go through that. That's negative b over 2 times a. So x equals 9/4. Okay, that tells me that my vertex is right around 9/4. And since it didn't come out clean, I'm just going to check points around there. This is just a little bit more than 2. So I'm going to test values around 2. I'm going to do 2, 3, 1, and maybe 4 as well. But we should get an idea of how the parabola is working using those points. Okay, they're not asking us for all the details. They don't need to know the vertex or anything, so we're not going to do all that extra work. If I plug in a 1, I get negative 2 plus 9 minus 4. Okay, that's positive 7 minus 4, positive 3. So my point is 1, 3. If I plug in 2, I get negative 8 plus 18 minus 4. That is a positive 10 minus 4. That's a 6. If I plug in 3, I get negative 18 plus 27 minus 4, and that comes out to be 9 minus 4, 5. And if we plug in a 4, I get negative 32 plus 36 minus 4. Negative 32 plus 36, that's 4, minus 4 is 0. Okay, so we can see our graph here. Do I make it a solid or a dashed parabola? Since it is greater than or equal to, it's going to be a solid parabola. And obviously, the tablet makes this a little bit more difficult. Now, we want to test a point. And I'm going to choose the point 1, 0. My graph was not incredibly accurate, so I don't know if 0, 0 is really inside or outside. I want to be sure, so I'm going to choose the point 1, 0 that I know is inside. Well, 0, the y value, greater than or equal to negative 2 times 1 squared. Okay, negative 2 plus 9 times 1, and then minus 4. So I get a value of 3. Is 0 greater than or equal to 3? No, it is not. So that tells me that this point I tested inside is not a solution. I must shade everything on the other side, on the outside of that parabola. And every single point that I'm shading here would solve that inequality. So it is graphed. All right, number 14. Here we've got vertex form, which is really, really helpful. Right, so we can jump right to our vertex. It's positive 1/2, positive 5/2. And I know it's going to open up, right? It's got an a value of 1. So we've got all these checks in place. And since my vertex is 1/2, 5/2, I can do negative 1, 0, positive 1. And how about positive 2 as well? And choose values around the x value of that vertex. So if x equals negative 1, then we're going to have a little bit of work on our hands. We got 1 minus 1/2. That's 1/2 squared plus 5/2. And 1/2 squared is 1/4, square the top, square the bottom, plus 5/2, which is 10/4. That gives me 11/4. If I have an x value of 0, then I get 1/2, negative 1/2 squared plus 5/2. Oh, hey, it's the same thing. It's going to be 11/4. And, wait a second. Oh, I did that wrong. The math I did was for positive 1, so positive 1 should have an output of 11/4. Shoot. Okay. Just going to erase that. All right, so this work actually went to this solution. This work goes to this one. If I plugged in a -1, here's where I went wrong. -1 minus 1/2 is -3/2 squared plus 5/2. So that's 9/4 plus 10/4, 19/4. Okay, let's see what happens if I plug in a 2. 2 minus 1/2 is 1.5, or 3/2 again, squared plus 5/2. And you can see that the squaring, it's the same work as up above because that negative sign vanishes. We get another 19/4. All right, so 11/4 is 2 3/4. And 19/4, that's going to be, 4 3/4? So there we can see our parabola is less than or equal to. So that means with the or equal to, we want a solid parabola. All right, and now we want to test a point. Hey, 0, 0 is clearly outside, so let's test 0, 0. And if I test 0, 0, 0 less than or equal to 0 minus 1/2 squared plus 5/2 is 0 less than or equal to 11/4. Yes, it is. So that means where 0, 0 is located, that's the area that gets shaded. Okay? Now, another way to look at this and kind of see if it makes sense is to, I apologize for how sloppy these look, I just kind of had to look at it, but another way to think about this is y means height, right? So if we wanted to check our work and see if it makes sense, here we want our height to be greater than, so a greater height means it's taller than the graph. So when we drew the graph, we wanted all the heights up above that graph included in our solution, so we ended up shading around. For number 14, here we want our heights less than this function, so when we draw in the function, we want the heights that are lower than the graph. So that's where we ended up shading. Sometimes it can get finicky using that logic, but it is a nice check. We do want to refer back to a ironclad test point to be certain. Example 2, a wire cable can safely support a weight W in pounds provided by, or got advertisements here, provided that the weight is less than or equal to 8,000 d squared, where d is the diameter of the cable in inches. Graph the inequality and interpret the solution. All right, so if we graph this out, we could make an input-output table of values. It's just d's and w's instead of x's and y's. 0, 0. And I'm only going to go positive because we can't have a negative weight. Anti-gravity has not been developed just yet. We get 1, 8,000. If we have 2, we get 8,000 times 2 squared. And if we have 3, we got 8,000 times 3 squared. 72,000. So what I'm going to do is I'm going to have my y-axis go by 8,000s. And my x-axis go by 1s. So we're 1 up 8,000. 2, we're up 8, 16, 24, 32,000. 3, counting by 8,000s, there is our parabola. And I'm giving it a solid parabola because my inequality was less than or equal to. All right, now if y is the weight, just think about that. Then I don't want a negative output, right? Again, we can't have negative weights. So this whole part is not included in the graph, nor is this part. We're really only looking in quadrant 1 where we would have a positive diameter and a positive weight. So I'm just going to change colors here really quickly. Our solution is this area of the graph. And we could test a point over here, like the point 50. Let's do that just to be sure. Okay, so the weight, the output 0, is that less than or equal to 8,000 times 5 squared? Absolutely. So we chose the appropriate region. Now here's what I think is really useful. Very rarely do you see really nice examples of this, real-world examples of this concept. This shaded region over here, that represents a place where the height on the graph, which means the weight of the object, is less than that inequality. That function is telling us the maximum weight that cable can hold. So anything that's shaded over there is the shaded region shows weights that can be safely supported by cables based on their diameter. So in other words, if we were, an engineer or like an iron worker or something, and we want to say, okay, our cable is 1 inch thick, can it support a weight of like 24,000 pounds? Oh, that doesn't fall in the safe zone. Or you could say, hey, we've got a cable that is 10 inches thick, can we lift a weight that is 16,000 pounds? Absolutely we can, that falls in the safe zone. So anytime we wanted to see before lifting that object, we could see, can the cable actually lift it? Very cool. Example 3, graph the system of quadratic inequalities. Well, let's start with the first one. Y is greater than or equal to x squared minus 4. Down at minus 4. And then using a table of values, we could construct that parabola. It's or equals to, so we use a solid graph. I take my time on this tablet here and try and make it as nice as possible. Okay, and we want heights greater than that parabola. We could test the point 0, 0, but what will be shaded in that graph is the interior, right? That's where the heights are higher. All right, let's get a different color up here. How about blue? Second one, y is less than or equal to negative 2x squared plus 7x plus 4. Okay, so let's just quickly find out what our axis of symmetry is there. Negative b over 2 times a. So we've got 7/4. That tells us where we can pick some smart points for our table of values. That is 1 3/4. So I could choose an x value of 1, I could choose an x value of 0, I could choose an x value of 2 and 3. That should give us a good look. If I plug in a 0, I end up with a y value of 4. If I plug in a 1, I get negative 2 plus 7 plus 4. So negative 2 plus 11, that's positive 9. That can't be right. No, it can be right. If I plug in a 2, negative 2 times 4, negative 8. Plus 7 times 2, 14, plus 4. Negative 8 plus 14 plus 4 is 10. If I plug in a 3, I get negative 18. Plus 7 times 3, plus 21, and then plus 4. I have a positive 3 plus a positive 4, that's 7. So I'm at 0, 4, there's 1 point. I am at 1, 9, there's another point. I am at 2, 10. another point, and 3, 7. There's another point. Again, this is an or equal to case, so I will use a solid parabola. Looks like that. And here we want all y values that are less than or equal to, all heights less than or equal to. So beneath that graph, that is indicative of all the y values inside. Now our solution, let's use a nice bright color, how about orange? Our solution is where those two inequalities overlap, where those shaded regions overlap. So everywhere inside here is our solution set, kind of a banana looking shape there. Example 4, solve the inequality algebraically. Now, you'll notice this is kind of like our introduction slide a little bit. There's no y's in there. We're not drawing a graph of a parabola and shading a whole lot. Here we're just looking where are the x values that make this function greater than -10. And our process will stay the same. We're going to treat it as if it were an equation. And then we'll test points. So obviously we've got a trinomial. So we want to get it set up equal to 0. And then we'll look, okay, is this factorable? 3 times 10 is 30. What multiplies to be 30 and adds up to -13, -3, and -10? Divide those by our a term and simplify. So I have x minus 1 and 3x minus 10 are the two solutions that would equal 0. So x equals positive 1 and positive 10/3. Okay, so we went through the factoring method. It's a lot less writing and simplifying than quadratic formula. Fewer places to make a mistake. Now what we need to decide is, do we want the values that are in between those two or outside those two? So you may remember this from Algebra 1 or even geometry. What we do is we plot those on a number line. So here we've got 0, and we've got 1, 2, 3, and then here is our 10/3. Now, it is just greater than, so I know those actual values are not included, the 0 and the 10/3. So I'll use open circles there. But then we just test. So it's either going to be inside or outside, just like with the parabola. And 1 is a nice, easy value to test. So 3 times 1 squared minus 13 times 1, is that greater than -10? 3 minus 13 is -10. Is that greater than -10? No. So we shade on the outside. And, you know, maybe, oh, that was really close. I'm not sure if that works. We could test 2 as well. You know, we want to be sure of our answer. So 3 times 2 squared minus 13 times 2, is that greater than -10? -14 greater than -10? No, it's more negative. It's less than. So that should confirm that we are not shading the middle region here. Our solutions are outside. So how would we write that? Our answer is all x values that are less than 0 or all x values that are greater than 10/3. And in interval notation, remember negative infinity is way off on the left on this number line. Positive infinity way off on the right. We're basically just looking at our x-axis. So from negative infinity up to 0, not including it. And we could also go from 10/3, not including it, to positive infinity. I would really encourage you to look at the interval notation when you get to pre-calculus or calculus in college. that tends to be the form that you look at. It's a lot easier to read. So if you can get familiar with it now, it's going to pay off. Okay, example 5, solve the inequality by graphing. All right, well, what we want to do is we want to treat this as if it were just a regular polynomial function set equal to 0. So if we were to graph this out, y equals x squared minus 4x plus 2, we'd probably start off by finding the axis of symmetry. X equals negative b over 2a. We find that's x equals 2. All right, and that's going to help guide our table of values to graph this inequality out. So I know I want my x values situated around 2. So I might do 0, 1, 2, 3, and 4. So what happens when we plug in a 0 into this function right here? So if we plug in a 0, we're going to get a y output of 2. So the point 0, 2 is on that graph. And hey, I can reflect that. Right? We've got those reflective properties. We don't need when x equals 4. Okay, how about when x equals 1? Well, then I've got 1 squared minus 4 times 1 plus 2. That equals negative 1. And I can reflect that. Hey, I don't need the x value of 3. We've got the symmetry working for us. And if we plug in 2, what we end up with is 2 squared minus 4 times 2 plus 2. That equals negative 2. So at 2, I'm down at negative 2, and we can see our parabola forming very nicely. Now, I want to solve this inequality. It's strictly greater than 0. So we want a dashed parabola. So I'll make a dashed graph there. And now, we don't need to shade any particular part of this, right? We don't want y greater than, our heights greater than the graph or less than the graph. We're concerned about the when, the x value. So when is this function greater than 0? And again, we're talking about the function's height. This is the whole thing. That is y. That is the height. So where is the height greater than 0? Well, right here it crosses, right here it crosses, and I see that the x values, the inputs on either side, if I go outward, those show me where the graph is up above, where it has a greater height. So if we think about the x-axis being the number line, like we saw in the earlier examples, what we've got is a situation where our solutions are around, we got somewhere in between 1 and 2, somewhere between 3 and 4, and then our solutions are going to be going out from those places. All right, so what we need to actually finish solving this is, what are those x values? As soon as we know that, we can set up our inequality to go outward from there. So let's look at the equation x squared minus 4x plus 2 equals 0. It's unfactorable, unfortunately, but we can use the quadratic formula. So x equals opposite of b plus or minus square root of b squared minus 4 times a times c. 4 times 1 times 2 is 8, all over 2a. Clean up under that radical sign. 16 minus 8 is 8. And we talked about this earlier, square root of 8. We can simplify that. That's a good one to know right off the top of your head. Square root of 8 is 2 root 2. It comes up an awful lot. All over 2. And now, since all of our loose numbers in the numerator match up or have the same divisor as the denominator, we can simplify that. 4 over 2 is 2. And 2 over 2 is 1. So 2 plus 1 root 2, or just 2 plus root 2. Plus or minus, I should say. So how does this look? Well, this is 2 minus root 2, and this would be 2 plus root 2. So we want x values that are less than, not including, right, that graph was dashed, less than 2 minus root 2, and we want x values that are greater than 2 plus root 2. So that's our solution using compound inequality. Or we could express that using interval notation from negative infinity to 2 minus root 2, not including it, and from 2 plus root 2 on to positive infinity. And again, we did not include that, so we used a rounded parenthesis there. Same solution, just different formats. And that does it for Chapter 3. Here's a look at your final assignment for this chapter.